Now, after Rolf's guest lecture, we'll continue with the actual content. So what we have done so far in this course is we looked into quantum mechanics. Today you saw some extra outreach from the CERN perspective on particle physics. Then we looked at how we can use quantum mechanics for computations in the architecture chapter. And we saw what quantum computers are able to do and what they are not really able to do, or where they don't provide any noticeable speed up. Now there are two challenges left that what we actually need to explore. One challenge is we need to be looking into concrete algorithms. That's one thing, because we not just want to do computations, but actually solve some real problems. And then after that, the next challenge is we want real quantum computers, and we not want to know how we program them. And then all of these challenges solved will lead to real applications. And today we will look at the selected algorithms, and in next week's lecture we will see concrete computer architectures and how to write code in order to run these programs on quantum computers, and there will also be a lab session. So we will look today at a couple of algorithms, and we will study them, some in greater detail, some from a more abstract perspective, and we will see some concrete challenges when it comes to algorithm design. So all the theories we saw so far look super interesting. And now you would think, well, there are lots of quantum algorithms and we can just solve a lot of problems in a much better complexity class. The reality is it's not that easy. There's a very interesting website, the Quantum Algorithm Zoo, and in the Quantum Algorithm Zoo, that's a collection of various quantum algorithms that have been proposed in the literature. And if you look at them on the website, so we also got a link here, it's a few dozens of algorithms that have actually been proposed in the literature. So it's just a few dozens. And if you look at the non-quantum world, so classic binary, obviously out there are thousands or tens of thousands of algorithms that have been proposed in the literature, and software engineers have probably developed millions of algorithms that are now running all over the world. But for quantum computing, it's different, because from these few dozens of algorithms that have been proposed for quantum computers, only probably a handful is actually usable or useful in the real world, because the others, so most also here in this quantum algorithm zoo, are actually just algorithms that are purely there for academic problems, but don't solve much of real problems. So feel free to go through this list. Maybe some of these algorithms could also be interesting with regards to your seminar presentation, but most of them are actually purely academic. Now, why is it that difficult to come up with new quantum algorithms? The challenge is you need to solve a problem, and you need to your quantum algorithm will be a combination of these fundamental operations we have studied so far, and you somehow need to put these fundamental quantum mechanic operations together so it solves a real problem, and it solves it more efficiently than with a classical computer. And it's probably way more complex to build something like that than if you, for example, just use binary computers and you start coding. We'll see if the coding part and how to turn these algorithms into concrete code that run next week. But first we need to come up with that algorithm. And in classic computing, you don't need to know about quantum mechanics. So what we have here is we're still at a very low abstraction level. And I think for quantum computing to become more useful and successful, we not just need better quantum computers and reduce decoherence, we also need more abstraction when describing algorithms. Because nowadays, what we do in binary or in classic computing is also we use high-level programming languages. We don't need to worry about individual registers and how to manipulate them, but we use some more abstract languages like Python or Java or whatever. But for quantum computing, we don't really have that abstraction layer yet. There are some attempts, but they are not anywhere to being that useful yet. And now let's see a few quantum algorithms. And before we look at them, we will see what a lot of them actually have in common. So essentially all quantum algorithms, or most of them, they have the following setup. We use, we access the quantum computer from outside, from the classic world. So this, we will put some of the qubits as inputs in some particular classical state, 0 or 1. And in the next step, we need to put some of these qubits or all of them into some superposition of many states. So because we need superpositions actually to speed up, to use superposition as as a parallelization. So we start with number one, qubits in the particular classical states, then create superpositions, and then start manipulating these superpositions with some unitary operations. We have seen some of them last week and in the week before. We need to combine them in some smart way so that it solves actually a real world problem and it gives us a massive speed up. And eventually we do a measurement. And with the measurement, the quantum system will collapse and we have classic outputs 0 and 1. Obviously, there are various variations to the scheme, but overall, I think this is more of a general scheme that you would see quite often. And that challenge is overall number 3. Which unitary operations get combined how, so we actually solve a real problem and it leads to a speed up and a speed up in terms of the complexity class. Now, you could try to visualize this, for example. So here we have classical inputs, 0, 0, zeros, and this is just another visualization of the measurement. There are different figures or different elements what a measurement could look like. We saw one last week. This is a different symbol that is quite common. And then in here, for example, we have some C-NOT gates, which are unitary, plus some other blocks. Maybe this one here could be a harder MUT gate or something, and this are some other unitary operations, and we would need to combine them in some way so we get some useful result for a real world problem, and we get a speed up, and eventually we measure, and then we get again classical values. I had added a few slides to this slide deck just a few days ago. I will upload the enriched slide deck next week when we finish the course. And overall, when you look at quantum computing, I've said this a few times in this course, but I just want to emphasize it. We deal with an inherently non-deterministic environment because we have the measurement, which is non-deterministic. So we run the same experiment multiple times, we get different outputs. Plus we have decoherence in real quantum computers, at least in the ones we have today, which adds even more uncertainty. We will also see more decoherence next week when we look in the course in concrete quantum computer architectures. So we see coming up with quantum algorithms is challenging because we need to know about which operations and how to combine them. Plus, the next challenge is decoherence. We've also seen last week that debugging is not really possible because for debugging, I would need to measure my qubits, but measurement means I collapse the quantum state. So that's also something that I don't really want to do. So it's quite tough to actually come up with real quantum algorithms and make them work. A friend of mine that I talked to, he was the CTO of a very large software company that all of you know, not saying which software company, but very large software company that you all know. And he stepped down a while back and I sat together with him a few months ago in some castle there was an executive meeting bringing people together for discussions, and he wanted to know my view on quantum computing, and he told me when he was still CTO of this very large software company, they had also started to explore quantum computing and invited a quantum computing startup from, I think, from the US, and they also told them that quantum computers were so helpful and they could solve a lot of problems. But when it came up when real problems came up that a large software company was working on, for example, in logistics, then that startup didn't really deliver much because they also struggled to come up with real algorithms that added value. And they weren't able to devise these algorithms, and eventually it didn't lead to any improvement. And he wanted to know my take on it. And I said, well, that's probably what would happen in such a lot of collaborations because we lack simply an abstraction. We need more abstraction. If we were today still in classic computing, in just dealing with bits and registers, probably we wouldn't have these extremely powerful computing applications today. So we need more abstraction because here, the understanding the low level stuff is even way more difficult than in classical computing. That's probably something to remember. Now we will look at a few quantum algorithms. One is the Deutsch algorithm. Why is it called Deutsch algorithm? It's named after Mr. Deutsch, a researcher. And I will tell you a little bit about what that algorithm is about. It's a very simple problem that you could look at. Imagine you have a function, and the function has an input, and the input is either 0 or 1, and it would map that input to either 0 or 1. And we can look at the four possible functions that come up from that setting. So I could have the first function that maps 0 and 1 to 0. The other function maps 0 and 1 to 1. Or the next function is that maps the 0 to 0 and 1 to 1. Or 0 to 1 and 1 to 0. So these are the four possible functions. Now for that setting, I want to know if one of these concrete functions that I have here is balanced. And the balanced function would be that f of 0 is different to f of 1, or the function could be constant, where f of 0 is f of 1. If you look at these examples, you as a human would see very quickly which of them is balanced and which of them is constant. And I want to determine now if such a function is balanced or constant with an algorithm. And this is purely an academic problem, but this toy problem was described in 1985 by Mr. Deutsch, and he showed that if we had real quantum computers, which at that time didn't exist, that this would actually lead to a speed up. So we could solve this problem here quicker with a quantum computer simply because of the superposition than with a traditional computer. But still, there's a speed up, but this problem can also be decided very, very efficiently by a classic computer. With a quantum computer, still a little bit better. But this is purely a toy problem without any real-world applications. A few years later, this problem was extended, and this is the Deutsch-Jozsa algorithm. It's a generalization of the Deutsch algorithm. What it does is, now imagine our function has n inputs, and each of the input is 0 or 1. So we have eventually a string of inputs, and they are 0, 1s combined in some way. And such a string would be mapped to either 0 or 1. And now now we will get a bit more specific that these functions, they would accept such a string of 0s and 1s and output a 0 or 1. And we would say that the function is balanced if exactly half of the inputs of the function go to 0 and the other half goes to 1, or such a function is constant if all the inputs go to 0 or all the inputs go to 1. Now, if I have a lot of these inputs, solving this for a large n with a traditional computer could be challenging, especially if the strings get super long and I have a lot of them. Concretely, with a classical computer, determining this is O of 2 to the power of n. But with a quantum computer, I would get an exponential speed up simply because of superpositions. So it's a toy problem, but way more complex than the Deutsch algorithm problem. And this was the first algorithm that would give us actually an exponential speed up. So we could solve this exponentially faster with a quantum computer. So massive speed up, but probably still a toy problem without much real world applications. There's also the Simon's algorithm, some other toy problem, and these three algorithms, so Deutsch-Jozsa, and Simon's, are described in the book. Feel free to look them up. Some students may pick this also as a seminar topic every year, one of these algorithms, and explains us in detail how these algorithms work. So after these toy algorithms, we will now look at two real-world algorithms that have real consequences. And one is the Crowver's algorithm. We had talked about the Crowver's algorithm in the very beginning of this course when we started. And what we explored was this black box search problem. So with the Crowver's algorithm, we have a black box function. We have n possible inputs, and we want to find that one particular input, which is the right, for which we get the answer of the black box. That's something we saw in the very beginning of this course. Now, if I have n possible inputs and one of them is exactly the right one, obviously I could be lucky that I solved this in O of 1 with the best case, because maybe the first one or the first k many I look at and I find that that one is the one I'm looking for. In the worst case, it's O of n, because I need to try all n possible inputs. So maybe the very last one is the one I'm looking for. And here I'm unable to sort the inputs or find any structure in them that I could exploit. And the average case is obviously O of n half, because in average I would need to look into half of them. But we care about the worst case, so it's O of n. And the Crowver algorithm would allow us to solve this problem in about square root of n times pi divided by 4 many steps. And this term here, so square root of n times pi divided by 4, is O of square root of n. But this is a probabilistic algorithm, so the Crowver's algorithm would find with high probability the solution, and the answer that is returned by the Crowver's algorithm could be wrong, because we're talking here about a stochastic algorithm, plus we have decoherence in the quantum computer. But what I would do is, if I get the answer by the Crowver algorithm, I would take that answer and put it into the black box as the input and see if that's actually the one that generates the desired output. If it does, I'm done. If I'm not done, I would run the computation again, because it is non-deterministic. I would get most likely a different output, and that's the one I would test again on the black box. And usually one assumes that just a couple of tries would probably return me the right result. So it's square root of n, but even if I need to run that experiment a few times until I find the right answer, it still would give me a massive speed up, especially if n is very large. The Crowver's algorithm, it turns out it's a highly generic algorithm. I could apply it to a lot of different search problems, not just to that one specific algorithm problem. But it doesn't give me an exponential speed up. It gives me a squared speed up, which is already massive, but it's not an exponential speed up. That's something very important to remember. But it's a highly generic algorithm that I can apply to lots of different problems. Now, if you want to learn more about the Grover algorithm, I mentioned it last week already. We will quickly open again the quantum.country, and there is a very long essay on the quantum search algorithm, so the Grover algorithm, and you can study in here in detail how the Grover algorithm works. Every year, one or two groups also pick this topic as a seminar presentation, and we want to leave you some opportunities for seminar presentations or in the lecture part. We don't discuss in detail how the Grover algorithm works, but feel free to look into this essay if you want to see it, and you will also see why this constant factor is pi divided by 4 because of some geometric considerations about vectors. But this is explained here in detail, and you will overall, by reading this essay, get a good overview about how the Grover algorithm works and why it leads to a squared speedup. Last week, I mentioned quantum.country. Did any of you study this interactive essay about quantum computing for the curious? If so, maybe send me a thumbs up or positive reaction. And if you have done this, feel free to send any comments here in the chat, whether this gave you any insights or what your learnings were. You can also just turn on your mic and tell us what you think about quantum.country or here in the chat as you wish. I'll see if anything still comes in via the chat. And as I said, take a look. You can study the Grover algorithm here in detail, plus have some questions in this interactive essay. Now, something that is quite interesting is now if we have larger and larger quantum computers available, we actually want to implement Grover's algorithm on such quantum computers and run it. The question is how many gates and how many operations do I actually need when I implement that Grover's algorithm on a real quantum computer? And maybe I want to have n sufficiently large, and then probably I need a lot of gates. And how many qubits do I need in a quantum computer? And there has been some recent research, concretely, I think earlier this year, and this is one of the slides I added as well a few days ago. Earlier this year, a paper got published. I have the link here in case you want to read it, and it shows that one would actually need less gates in the quantum circuit when implementing the Grover algorithm than many people thought before, because we have this very abstract algorithm and we need to turn it into something concrete and implement it. And now it's been noticed that we would actually need less gates than we believed before when implementing Grover's algorithm. So that's something that is quite interesting and also helpful to make quantum computers or quantum computers more useful, because we have quite a limited number of qubits, but we need less qubits to implement certain algorithms for a specific input size. So that's something quite interesting that got published earlier this year, and probably this will trigger more papers of that sort. While Grover's algorithm is a highly generic algorithm that gives us a squared speedup, there is something more specific, and that's concretely the Shor's algorithm. And Shor's algorithm does the following. So a lot of encryption methods that we use nowadays, they are based on the fact that we have some integer n, and that n is the product of p and q, where p and q are prime numbers. And now if we have n, which is a very large number, so the product of two large prime numbers, we want to do a factorization and want to figure out what n is made of, which are these two prime numbers. In classic computing, this takes a lot of time. For example, exponential time, or slightly below exponential if you use, for example, a general number field sieve. But for the general field number sieve, we have this complexity here, which is quite ugly to read out. But this is still extremely inefficient with a classical computer, because it runs, even if with the general number field sieve, which makes some constraints, or we just use this in a naive way. Either way, it's taking super long, and that's why for large keys, we are unable to crack that encryption today. Now, with the Shor's algorithm, This gets suddenly solved in polynomial time. So we get, if we compare it against the general number field sieve, an almost exponential speed up. If we compare it against the naive method, which is more universal, we would get an exponential speed up. So the Shor's algorithm leads to a massive speed up. It's not generic. We can only apply it to integer factorization, but that means as we have larger quantum computers available, we would be able to crack a lot of encryption methods that are common today. And when we started this course almost 2 months ago, I also said that there are three post-quantum encryption methods that cannot be cracked efficiently by quantum computers, and they got standardized, and there's now this NIST standard, and IT vendors have started to implement them in their solutions. So IT companies can slowly migrate now to post-quantum encryption because we don't know when that day is coming when we have much larger quantum computers available. It's uncertain, and we will see this next week when we look at computer architectures and see how we can program them. But we see it leads, once we have this available, this would end today's encryption. And that's why it's early to that's why it's important to transition early. And now, because there are three standards available, IT vendors can slowly start implementing, and we can start slowly migrating. And for example, I think with the Apple messages, they have, so the iMessage, they have announced such a migration, as well as some others already. So it's coming step by step. So when that day happens, and we don't know when it's happening, we have already migrated. So that's something that is currently important in IT security. Now, let's compare these algorithms. We've looked at Deutsch, we've looked at Deutsch-Jozsa, as well as Grover's and Shor's. When we want to compare these algorithms and assess, I have four properties here that we want to look at. There's the first property that we call performance. And performance here doesn't mean speed, but performance in this context means that the algorithm solves a task well. So that the algorithm solves the task it's supposed to solve. Then the second property is speed up. So it's that the algorithm runs faster than classical competitors, ideally better than in a better complexity class and not just by some factor faster. Relevance means that the algorithm solves a problem that is practically relevant. So most of the algorithms from the quantum algorithm zoo I mentioned earlier, they are probably not relevant, purely academic. And then there's another property, which is availability. And availability would mean that the technology to implement the algorithm for a sufficient input size has the reasonable chance to be available sometime in the foreseeable future. So we can actually implement it on a quantum computer that is large enough. Now, if we look at the four algorithms we saw, we can think about this quantum advantage. And quantum advantage here means if all of this is satisfied, then the quantum computers would actually add some real benefit because we solve a real problem that is relevant and we solve it faster, and the technology is available in the foreseeable future. There's this term quantum advantage. Some people use a different term that is called quantum supremacy, means more or less the same, but I think quantum advantage sounds overall probably less troubling than quantum supremacy or quantum supremacy. Now, the Deutsch algorithm, so remember just the 0, 1 gets mapped to 0, 1. The algorithm solves that problem. It runs faster than on a classical competitor, maybe not with a massive speed up, but at least some limited speed up, but it's not relevant. And maybe for something like this, that's something we can implement on a quantum computer today or in the foreseeable future. Now, if you look at the Deutsch-Jozsa algorithm, yes, it solves a problem, but that problem is not very relevant. we even get an exponential speed up. And if the n is not too large, that's something we could be running on a quantum computer in the foreseeable future. For super large n, obviously, we may need way more qubits, and then it may still be out of reach. But how many qubits we got available, that's something we will see next week. Then the Grover's algorithm is solves a task well, which is the black box problem. Obviously, we saw that the answer may be wrong and we have to run it again. But that problem or the issue of uncertainty, or here non-determinism, it applies to all the quantum algorithms because what we do is highly non-deterministic. So it's not a limitation exclusively of the Grover algorithm. And the Grover algorithm leads to a speed up, not exponential, but a squared speed up, solves actually a real world problem, actually can solve a lot of real world problems, a lot of search problems. But when we would have that available, at least for sufficiently large n on real hardware, that's currently unknown. We just don't know. And we will see next week some roadmaps of IT vendors, how many qubits they aim to have in the next few years. So this is a bit uncertain when this would actually happen. But we'll see these architectures next week. And we can make sort of the same considerations for Shor's, because Shor's solves a problem well, integer factorization. It's a relevant problem, leads to a near or actual exponential speed up. But again, it's unclear when we would have such quantum computers available on which we can actually run this. Now I'm halfway in my career. You're at the beginning of your career. You still got many years to work. Me too. We will simply see in the next few years or decades when this would materialize. And this course is also meant to prepare you for this quantum future. So as quantum computers become more powerful, and maybe we can program them more easy in a more abstract way, then all of this could really take off. But you now have the foundations to see or to be prepared for this future. And every year, some students present selected algorithms like the 4 I have shown or more from this quantum zoo. Now, we will continue next week with the lectures, since today, most of the lecture time, we had Rolf's guest lecture, about which I'm very happy. And today we don't have enough time to finish these last 2 chapters. So next week we will focus on real quantum computer architectures and how to program them. We will also see the issue of decoherence in greater detail, and we will see a few more applications where quantum computers look promising. And when we finish this next week, I will also say a few more words about the seminar presentation, my expectations. You could have some questions about potential topics. And then we discuss the roadmap for the next few weeks, when you need to submit by when and when you need to present what. But I had communicated these dates anyway already a long time ago, and I learned, but next week we look at all of these deadlines together. If you got any questions, maybe just raise your hand now here in Zoom if there are any questions before the end today. And with there not being any questions, we are done for today. I wish you a great weekend, and next week we'll finish the course. What I will do now is I will share the evaluation link in iLearn, and it's your opportunity to evaluate the course, because we've also finished most of the computing stuff. And next week you will simply see concrete quantum computers and how to write code for them. There'll be some demo. So that's something we haven't done yet, but this will come next week. And I look forward to your course evaluation. Thank you very much and enjoy the weekend. Bye-bye.